Over 700 million tons of sugarcane bagasse are left forgotten, piled high like mountains after every crushing season. Yet a global biomass revolution has risen, transforming this abandoned waste into the new generation of green gold, worth billions of dollars. This miraculous rebirth begins in vast sugarcane fields, where millions of tons of cane are harvested in the rush of the sugar season. After being pressed to the last drop of sweetness, the seemingly worthless bagasse continues its journey into modern recycling facilities, where advanced technologies revive every fiber into promising bio-based materials of the future. Don't take your eyes off this video, because up next are the most valuable insights into the hottest recycling industry today, and the secret behind sugarcane bagasse's rise to becoming the leading green material of a new era. Let's begin. By 2025, the agricultural byproduct recycling industry has surpassed $420 billion. Sugarcane bagasse alone contributes 18% of that value, second only to rice straw. At the top of this value chain stands Brazil, the sugarcane giant that dominates the sector with more than 210 million tons of bagasse recycled each year. Though far from matching Brazil's scale, India and China remain noteworthy contenders, rapidly rising with booming bagasse-based paper and green packaging industries. To satisfy humanity's massive demand for sugar, more than 1.8 billion tons of sugarcane are crushed each year. And for every ton processed, roughly 300 kilograms of bagasse are discarded, while the sugar extracted amounts to barely 1/3 of that. In other words, the annual mountain of waste is so enormous that if piled into a single mass, it could reach the height of Japan's Mount Fuji. Yet to this day, only about 30% of that bagasse is properly recycled. The majority is burned or left to rot, generating fine dust and CO2 emissions that can exceed those of traditional plastics over a comparable life cycle. As environmental pollution grows into a global burden, from mountains of waste to rising CO2 in the air, the demand for truly sustainable materials has never been more urgent. In this context, sugarcane bagasse recycling is increasingly seen as a promising new pillar of sustainability. But whether it is genuinely green depends entirely on the technology and how every fiber is handled. A single misstep can overturn all its benefits and turn them into negative impacts. And that's exactly why you're here, to uncover how humanity is working, step by step, to turn waste into the future, sustainably. Our first stop is the bustling sugarcane fields at harvest season, the origin of this entire journey of rebirth. Before each harvest, many farmers in South America still choose to treat their sugarcane fields with fire, clearing dry leaves, driving away insects, and cleaning the stalks. Although burning sugarcane allows for faster harvesting, the environmental consequences cannot be overlooked. In Thailand and Brazil, the smoke from burning creates black smog, a dark haze stretching for dozens of kilometers, paralyzing traffic and forcing schools to close. More dangerously, just a single spark caught by strong winds is enough to consume an entire field. Many regions are forced to restrict burning to after 5 p.m., under strict supervision, to prevent the sugarcane fields from turning into a sea of fire. Due to these consequences, many countries are gradually restricting sugarcane burning and shifting toward a more environmentally friendly solution: fresh harvesting with modern machinery. In modern sugarcane harvesting, the first step is cutting the stalks close to the ground using a specialized blade assembly. Thanks to intelligent sensor systems, the machine can automatically adjust cutting depth, travel speed, and leaf blowing direction, ensuring the roots remain unharmed while keeping the stalks clean and low in impurities, a crucial factor for maximizing extraction efficiency at the mill. When cut correctly, sugarcane can regenerate from the same root for 3 to 5 consecutive seasons, helping farmers significantly reduce replanting costs. Right after cutting, the cane moves into the central processing system. Leaves are separated or chopped and returned to the field, while the stalks are uniformly segmented and transferred onto a conveyor system that loads them onto collection trailers. Notably, the harvester is also equipped with an automated hydraulic arm, allowing it to gather and unload cane into the trailer with precision, all without stopping the machine, optimizing the entire harvesting process right in the field. After harvest, the sugarcane is transported to the mill as quickly as possible by truck or train, because within just 24 hours its sugar content can drop by up to 15% due to dehydration and natural enzymatic breakdown. At modern sugar mills, thousands of tons of cane are received each day and moved into the pre-processing area. All incoming cane is accumulated on large storage yards or continuous conveyor systems. When processing begins, the cane is fed into intake hoppers and directed toward the primary handling equipment. Before pressing, the cane passes through a high-pressure water spray system that thoroughly removes dust, soil, and any surface impurities. Tiny grains of sand, seemingly harmless, can wear down the steel rollers and damage an entire multi-million-dollar mechanical line. The wash water is then recovered and treated in a closed-loop system, because even a small amount of bacterial contamination can cause the juice to ferment prematurely, ruining the entire batch of sugar from the very first stage. This is why the washing step, though simple in appearance, plays a critical role in the whole sugar production process. After the cleaning stage, the freshly cut cane is fed into the shredding system. Here, high-speed rotating knives continuously cut, slice, and tear open the tough outer rind while breaking down the inner fiber structure. This process softens the cane, increases its surface area, and exposes the sugar-bearing fibers within. By loosening the material and opening the cell walls, the shredder ensures that the downstream crushing mills can extract juice far more efficiently and with maximum yield. Next, the entire stream of material moves into massive, multi-roller crushing mills, equipped with a multi-stage roller assembly operating on a progressive compression mechanism under immense pressure. From here, a curious separation begins. The sweet cane juice becomes the next raw material for producing sugar, the white gold that sustains an entire industry. What remains, dry, fibrous, and seemingly lifeless, is the bagasse. Yet with modern technology and a new mindset, these discarded fibers are now collected and reborn, beginning a different journey, where waste is no longer the end of the story. Right after the juice is fully extracted at the sugar mill, thousands of tons of dry bagasse are gathered into massive outdoor piles. In countries where the sugar industry operates year-round, these bagasse hills can reach 5 to 6 meters in height and stretch across hundreds of square meters. The drying process may seem simple, but it is an extremely critical step. Excess moisture, if not removed properly, can cause the bagasse to rot, develop mold, or even ferment, leading to losses of tens of thousands of dollars. With natural sunlight and good ventilation, this drying period can last from several hours to a few days, depending on the weather and the thickness of the pile. Once dried, the bagasse is collected using loaders or conveyor systems and transferred onto specialized trucks. From there, it is transported to recycling facilities or biomass processing plants, where the material is revived and transformed into higher-value green products. At the recycling plant, the bagasse is received and carried directly inside through a continuous conveyor system. The first step, and one of the most critical, is cleaning the material. Here, the bagasse passes through a high-pressure water spray system to remove soil, sand, shredded cane fragments, and any remaining sugars clinging to the fibers. After washing, the material is mechanically dewatered or lightly dried to reduce its moisture content, creating ideal conditions for the subsequent grinding stage. The milled bagasse fibers are heated to 130 to 180 degrees Celsius, then blended with a small amount of natural starch or recycled pulp to improve flexibility and prevent cracking. Even in tiny quantities, these additives are key to turning the fibers into a strong, mold-ready biomaterial. After the refining process, the semi-liquid bagasse mixture is fed into specialized metal molds, preheated to 160 to 200 degrees Celsius. These molds are engineered with absolute precision for each product shape, from spoons and food containers to cups. When the mold closes, high pressure compresses the mixture into its final form, creating a solid structure through heat and compression alone, without the need for any chemical adhesives. When the hot pressing stage is complete, the product has taken shape but remains soft and firmly attached to the mold. It is sprayed with high-pressure cold water to cool it rapidly and assist with demolding. The entire mold set is then immersed in a vibrating water bath, where swirling currents cool the product completely and allow it to release smoothly from the mold without cracking or warping. After being dried to stabilize its moisture content and increase surface rigidity, the product becomes fully formed, sturdy, and ready for the trimming stage. At this stage, the excess edges formed during hot pressing are cleanly removed using specialized trimming blades. These high-speed cutters are calibrated for each mold design to ensure sharp, precise cuts without distorting the product's structure. The edges are then smoothed either by automated machinery or by skilled workers, eliminating any remaining fiber burrs, small details that can affect handling comfort and overall safety. In more advanced facilities, this entire process is fully automated through robotic systems. Integrated cameras and optical sensors continuously scan the product's surface, detecting even the slightest irregularities along the outline. The robot then adjusts cutting force, angle, and speed in real time, creating perfectly consistent edges that manual trimming could rarely achieve. Skipping this step would leave sharp or uneven edges on the product, compromising not only its visual quality but also its safety. Such imperfections can tear packaging during transport, scratch the user's hands, or create discomfort when the product comes into direct contact with food. For these reasons, edge trimming is an indispensable stage to ensure the final product meets rigorous standards of quality, safety, and user experience. Finally, the surface of each product is coated with a bio-based waterproof layer made from plant waxes or natural polymers. This ultra-thin coating allows bagasse items to withstand high temperatures, oily foods, and even liquids without absorbing moisture, softening, or deforming, an advantage conventional paper products simply cannot offer. Next, every plate, spoon, or container passes through a quality control system before being counted, sorted, and packaged by workers using recycled paper or cardboard to minimize environmental impact. From the production line, these items, once nothing more than agricultural waste, are shipped to supermarkets, restaurants, and food outlets around the world, where they replace single-use plastics with a solution that is sustainable, safe, and emblematic of modern green innovation. Have you ever wondered why products made from bagasse feel as sturdy as plastic while still being environmentally friendly? The secret lies in the way cellulose fibers naturally bond with one another under high heat and pressure, forming a kind of bioadhesive created right inside the mold. In theory, products made from bagasse can fully biodegrade in just 60 to 90 days, an impressive figure compared to traditional plastics, which can take 500 to 1,000 years to disappear from nature. But the reality is more complex. This rapid biodegradation occurs only under industrial composting conditions, where moisture, temperature, and microorganisms are carefully controlled. If discarded in a typical landfill, where oxygen and sunlight are limited, even organic materials can take many years to break down and may even generate methane in the process. Therefore, whether a product is truly environmentally friendly depends not only on its material, but also on how we dispose of it after use. For decades, Indonesia, the Philippines, and India have been the undisputed leaders, commanding over 70% of global coconut production. Yet in the arena of byproduct recycling, India stands as the true powerhouse, processing more than 500,000 tons of coir and cocoa peat each year and steering this billion-dollar industry. As the green living movement accelerates worldwide, demand for coir and cocoa peat has surged by 15% annually. What transformed materials once dismissed as agricultural waste into a global phenomenon? It starts with a natural paradox. Coconut fiber is organic, yet as tough as synthetics. Biodegradable, yet slow enough to endure 2 decades before breaking down. Combined with the coconut's near-zero waste nature, these traits have turned its byproducts into a genuine green goldmine. On the benefit side, recycling 1 ton of coconut husk can cut up to 250 kilograms of CO2, but left to rot or burned, that same husk releases methane, CH4, a greenhouse gas 28 times more potent than CO2. In a world facing escalating environmental crises, recycling coconuts is not only an ecological rescue but a remarkably smart way to turn waste into a multi-billion-dollar opportunity. Thousands of products are now born from coconuts, from construction materials, carpets and mattresses, to cosmetics and even road surfaces. Hard to believe? And that is exactly why you're here, to begin this remarkable journey of renewal. Back to the tropical coconut groves, where every new life of the coconut begins. Coconuts are not exactly a cooperative fruit. They grow in heavy clusters, clinging to the tops of 20 to 25-meter trees, turning every harvest season into something of an adventure sport, where a single unlucky slip could easily cost a picker a few non-replaceable components. If in the past, farmers had to gamble with safety by climbing straight up the tree or using long poles to hack down the bunches, both dangerous and prone to cracking the fruit. Today, they have a far smarter solution. Long harvesting poles, designed for just the right reach and tipped with curved blades that are sharp yet flexible, have become the ultimate tool. One clean sweep from an outstretched arm is enough to send a 30-kilogram cluster crashing down. The transportation method is just as ingenious. Shallow irrigation channels dug between coconut rows act as natural shock absorbers, catching the falling bunches from tens of meters above while preventing almost all surface damage. The coconuts are then gathered directly on the water, tied into floating chains like buoy lines, and towed back to the collection point. And that is only the beginning, because once the fresh coconuts reach the processing plant, their second life truly begins. A peeling journey that reveals the precious 30% inside, while the remaining 70%, that rugged outer armor, is reborn as coconut fiber. Thousands of tons of coconut husks pour into recycling plants, stacked into massive mountains, and left under the sun for several days to reduce moisture and soften naturally before entering their transformation phase. Once they reach the ideal dryness, these seemingly useless shells are fed into industrial shredders, where blades spinning at 1200–2800 RPM relentlessly tear, slice, and break apart the tough outer layer. Thanks to the strong cutting force and multi-tier steel blades, the machines can process tons of material per hour, producing a mix of long fibers and fine cocoa dust. This step is critical. The looseness and uniformity achieved during shredding directly determine the efficiency of subsequent cleaning, drying, and fiber separation stages. Fibers that meet the standard move on to screening systems to remove dust before being sun-dried or heat-dried to reach stable moisture levels. Once complete, the coconut fiber becomes a light, durable, and resilient material, ready to be reborn as mattresses, carpets, growing media, or countless other sustainable bioproducts. After being separated from the outer husk, coconut fiber is spread across large drying yards to soak up natural sunlight, preparing it for the next crucial stage, carding. Here, fast-moving cone rollers separate clumps, stretch the fibers, and align them into smooth strands. The result is a clean, uniform fiber stream, making carding essential for the consistency required in later twisting and weaving steps. After being finely carded, the coconut fiber is transferred to the spinning system. Here, the fiber bundles are twisted into small ropes or high-strength yarns, with each rotation tightening the strands and building the durability required for demanding applications. The twisting process binds the fibers firmly together, producing cords that are strong, resilient, and capable of withstanding significant tension. These cords become the core material used for weaving coir mats. Every parameter, twist level, diameter, density, and tensile strength, is closely monitored to ensure exceptional consistency, giving the final mats superior longevity, structural stability, and outstanding surface grip. Once the finished coconut fiber yarns are ready, they are fed into large weaving frames to form mats with the required thickness, density, and decorative patterns. In this stage, the warp threads are stretched tightly across the loom, creating a firm backbone for the mat, while the weft threads are passed rhythmically through each gap. Layer by layer, the two systems interlock to build a dense, stable structure that gives coir mats their signature coarse texture and remarkable durability. Every movement of the loom, whether powered by hand or machine, is calibrated to maintain tension, spacing, and uniformity. This precision ensures that the mats remain resistant to wear, maintain excellent grip, and hold their shape even under heavy use. Weaving is the defining step where craftsmanship and mechanical accuracy converge, shaping raw fiber into a finished product. Once the weaving is complete, the mats proceed to trimming, edge reinforcement, surface finishing, and final packing for shipment. In many traditional workshops, coconut fiber ropes are spread evenly across the floor before entering the sheet forming stage, using a wooden framing tool. This specially crafted frame functions like a hand-driven mechanical mold, with parallel wooden slats set at fixed intervals to guide craftsmen as they pull each strand into place without misalignment. Every lift and drop of the frame applies just enough pressure to lock the fibers in position while forming clean, straight channels across the surface. As the frame moves, workers use wooden mallets to tap rhythmically along the mat, compressing each layer of fiber to create a uniform structure, reduce air gaps, and maintain an even thickness. The process demands a precise understanding of force, rhythm, and fiber tension, skills gained only through years of experience. Through the harmonious combination of delicate craftsmanship and the intelligent design of the wooden frame, the finished coir sheets emerge strong, yet breathable, ready for the next stage of mattress pressing or mat weaving. Yet, the production process does not end there. The light, loose fibers left behind after weaving, too thin and lacking the structural cohesion required for mattresses or mats, are collected separately and routed into an entirely different manufacturing line. Here, this material, often dismissed as mere byproduct, becomes the ideal input for modern thermoforming technology. Golden bundles of fiber are evenly spread across heavy steel molds, forming a precise base layer. When the mold closes, the fibers are subjected to intense pressure, typically between 3 and 8 tons, combined with high heat. Under these conditions, the natural lignin within the coconut husk softens and flows, binding the fibers together from within. This unique mechanism allows the material to take shape without the use of any chemical adhesives, relying solely on the coconut's own organic resin. Only a few seconds later, the mold opens to reveal fully formed biodegradable coir pots. Lightweight, breathable, well-drained, moisture-retentive, and capable of breaking down completely in soil within months. Their naturally interwoven, root-like fiber structure allows plant roots to penetrate the pot walls easily, avoiding the circling and constriction commonly seen in plastic containers. Though these pots cannot match synthetic materials in long-term outdoor durability, they dramatically reduce plastic waste and are increasingly favored by growers and nurseries worldwide. Today, these coir-based containers are exported to more than 40 countries, becoming a small but significant part of the global shift towards sustainable horticulture. The newly formed pots are then moved to the finishing table, where any excess edges are trimmed cleanly to achieve a precise, uniform shape. Each pot undergoes a final inspection for thickness, compression, and surface quality before being packed, completing the coir fiber's transformation into a fully biodegradable product. But the journey of coir doesn't end there. Humble as it has become a key material in sustainable road construction thanks to its elasticity, drainage ability, and strong soil-binding properties. Before the coir layer is installed, the roadbed is cleared, moistened, graded, and compacted to the required density. Once the roadbed has been compacted, large coir sheets are laid evenly across the surface. Workers stretch each sheet along the alignment, overlap the edges, and smooth out the entire layer so it conforms tightly to the terrain. After the sheets are positioned, metal stakes are driven through the edges to secure them in place, creating a natural stabilization layer. No plastic, no waste, and at a cost up to 60% lower, making it ideal for rural roads where budgets are limited. With the sheets anchored, the coir immediately begins to do its job, holding soil in place, reducing surface slippage, limiting edge erosion, and dispersing loads across the subgrade. Though biodegradable and temporary, this very trait makes it a sustainable material that leaves no waste behind once its purpose is fulfilled. Immediately afterward, a truck spreads crushed stone evenly over the coir layer. The stones settle through the fiber mesh and lock into its natural structure, forming an effective mechanical interlock. After the layer of crushed stone is compacted by the roller, workers spread a layer of soil over the surface to fill the gaps and increase the stability of the roadbed. A final pass of the roller then locks the entire structure into place, forming a solid foundation for the layers that follow. Finally, asphalt is laid over the compacted base, completing the road surface with a durable, weather-resistant finish. From coarse fibers on tropical farms to mats, mattresses, plant pots, and even sustainable roads, coconut coir is now woven into everyday life around the world. Each year, the coir and cocoa peat industry alone generates more than $4 billion for producing countries, transforming what was once dismissed as agricultural waste into a true green gold mine. And this journey is far from over. As the world accelerates toward sustainable living, the future of coir will only grow broader, brighter, and more promising. Although natural rubber is now closely associated with Asia, its origins trace back to the dense Amazon rainforests. For centuries, indigenous peoples of Central and South America tapped the latex of Hevea brasiliensis to create waterproof coatings in everyday household items. But the global turning point came only after a covert smuggling of rubber seeds out of Brazil, an act that paved the way for the tree's introduction into Southeast Asia. Just a few decades later, the region rose to dominance, producing more than 90% of the world's supply, with Thailand leading the industry and exporting rubber worth billions of dollars each year. Natural rubber stands out for its exceptional elasticity, durability, and water resistance, making it an essential material for transportation, healthcare, and thousands of industrial products. Just 10 kilograms of fresh latex are enough to make a single car tire. But producing a latex mattress requires over 100 kilograms of latex, resulting in a material capable of withstanding pressure, many times a person's weight, and instantly returning to its original shape. And now, let me take you to Southeast Asia, a region with a humid tropical climate, fertile basalt soil, and year-round rainfall, all perfectly suited for rubber tree cultivation. Here, the trees are propagated using bud grafting. High-yield budwood from elite mother trees is grafted onto vigorous rootstocks that have been grown for 8–10 months. This ensures the next generation inherits the mother tree's superior genetics, a crucial factor behind durable plantations and exceptional yields. Young plants are placed in polybags, with soil packed firmly around the base to keep the stem stable. The natural outdoor environment helps them adapt early to sunlight, wind, and rain, reducing shock when they are finally transplanted into the field. After about 1 year, the young trees develop sturdier stems, their leaves darken, and the petioles begin to lignify, signaling that they are ready for planting. Unlike many other industrial crops, the most common cultivation model for natural rubber in Southeast Asia is the smallholder system. Each household typically owns only a few hectares of land, yet many have cultivated rubber for generations. Alongside these small holdings are vast plantations owned by state enterprises and private companies, spanning tens of thousands of hectares and managed under standardized, unified planting protocols. Every spacing measurement is carefully calculated. Nothing is done at random. In flat areas, rows are typically spaced about 6 meters apart. On sloped or moist terrain, spacing is reduced to 4 meters to limit erosion and make better use of shade. On average, each hectare contains 500 to 550 trees, dense enough for good canopy expansion, yet open enough to ensure strong root development for decades of tapping. Tapping latex is the most delicate and patience-demanding stage in the entire life cycle of a rubber tree. Before reaching this moment, the tree must undergo 6 to 7 years of continuous care until its trunk reaches a circumference of 45 to 50 centimeters and a bark thickness of 6 to 8 millimeters, just mature enough to open its first tapping cut. In specialized farming regions, tappers begin their work quietly from midnight to dawn, when the air is cool and moist, and the latex becomes thicker, smoother, and flows most evenly. The latex vessels always run from upper right to lower left, so the tapping knife must be held at a precise 45-degree angle to follow the correct direction. Before tapping, workers mark 3 to 4 guiding lines using a pen and measuring tool, or press a plastic stencil against the bark to ensure perfect alignment of the cut. When the knife is drawn, its thin curved blade slices only about 1 millimeter deep, just enough to reach the latex vessels without touching the wood. A slight slip of the hand can cause the tree to bleed, dry out its latex vessels, or lose vigor. The latex drips into aluminum or corrosion-resistant plastic cups hung about 15 centimeters below the tapping cut, close enough to catch the entire flow, yet far enough to avoid contamination. After 4 to 6 hours, the cups fill and are collected into larger containers. Over time, the cups build up an oxidized rubber film, which must be cleaned regularly. A skilled tapper can work 400 to 500 trees in a single morning, the result of years of practice to master the rhythm of each stroke, the exact depth of the cut, and the distinctive snap sound of latex vessels being opened. Across southern Thailand, thousands of small factories work day and night to press fresh latex into latex sheets. Thin, pale, flexible, and resilient layers of rubber that carry the vitality of the tropical forest and serve as the foundation of the global rubber industry. As soon as the fresh latex arrives, it is roughly filtered and poured into large aluminum trays. Workers stir it thoroughly to disperse the latex particles, then add a formic acid solution, the catalyst that helps the latex coagulate quickly. Within just a few minutes, the liquid begins to solidify into a smooth, soft, milky white mass. The surface is carefully leveled to ensure uniform thickness before the block is removed from the mold. This marks the very first step in forming a complete latex sheet. Once the latex has coagulated, each sheet is removed and rinsed in a water tank to eliminate any remaining acid. The sheets are then fed through a rolling machine, two heavy steel rollers spinning in opposite directions that press the rubber flat and bring it to the correct thickness. With every pass, water and impurities are squeezed out, making the rubber clearer, more flexible, and more elastic. The fine mesh-like patterns that appear on the surface are the hallmark of a properly rolled latex sheet. After rolling, the wet sheets are hung outdoors to dry. Depending on the weather, this air-drying process takes 1 to 2 days. At this stage, the rubber has become strong enough to fold, roll, or move without tearing. The dried sheets are then moved into the smokehouse. Smoke from smoldering firewood or wood chips drifts through the chamber, both fully drying the sheets and tinting them with their signature amber color. This process also provides antibacterial protection, prevents mold, and enhances durability. When they step out of the smokehouse, each sheet has taken on a golden hue, flexible, tough, and ready to be baled for shipment. Once they reach the proper dryness, the latex sheets are pressed flat, graded, and bundled into neat square bales. From there, they are sent to major factories, where these golden brown latex sheets will be transformed into tires, gloves, or durable shoe soles. All of them begin with a stream of white latex deep in the forest. Farewell to the smoky, wood-scented workshops. In modern factories, natural rubber latex is reborn as the core of some of the world's finest premium mattresses. Unlike memory foam, natural latex is inherently antibacterial, breathable, hypoallergenic, and offers outstanding elasticity and longevity. That's why, in the luxury segment, a king-size latex mattress can reach prices of up to $2,600 USD. First, natural latex is combined with various additives, such as foaming agents, stabilizers, sulfur, and accelerators. This mixture is blended thoroughly in specialized mixers to ensure uniformity and achieve the desired physical and chemical properties. This step determines the mattress's elasticity, durability, and its ability to form a stable foam structure in the next stages. Next, the uniform latex mixture is poured into a specialized mold fitted with metal rods called pincore pins, which create ventilation holes throughout the mattress. These holes enhance elasticity, airflow, and breathability, helping the mattress stay cool and comfortably supportive during use. Inside the vulcanization chamber, the latex mixture is heated and subjected to high pressure. The very breakthrough that gave birth to the modern rubber era more than 180 years ago. Heat and sulfur create cross-links between the polymer chains, transforming the soft, sticky liquid latex into a solid mass of elastic, stable, and durable rubber. Thanks to this process, the mattress core maintains its shape, resilience, and consistent foam structure for many years, a key requirement for it to qualify as a true industrial-grade product. When the process is complete, the mold is carefully opened after 1 to 2 hours of cooling. At this stage, the mattress is still soft and warm. Even a slight pull or a sudden impact can tear the surface, damage the ventilation hole structure, or cause deformation. For that reason, every movement must be slow, steady, and perfectly coordinated to ensure the mattress maintains its shape and surface integrity. After demolding, the mattress passes through a continuous, gentle washing system using clean water. Large rollers rotate slowly to turn and lightly press the latex block, allowing water to wash evenly across the surface while pushing out foam residue and impurities. This step ensures the mattress is not only thoroughly clean, but also safe, hypoallergenic, and user-friendly. The clean mattress then travels along a conveyor into a temperature-controlled drying chamber, which removes all remaining moisture, prevents mold growth, and preserves both the natural elasticity and stable foam structure. Before leaving the factory, each mattress is tested using an automatic pressure compression machine, a device capable of simulating tens of thousands of real-life sleep cycles. The machine repeatedly compresses and releases the mattress in a standardized rhythm, precisely measuring its sinkage, elasticity, and recovery ability. All data is recorded automatically. Only the products that pass this rigorous evaluation are approved for packaging and distribution. After passing inspection, the mattress is packaged with protective wrapping, vacuum sealed or rolled, depending on the model, then labeled, sealed, and shipped, ready to begin its journey to the consumer.